In previous lessons in this series on electromagnetic induction, we've looked at Faraday's law and Lenz's law. Now we're going to continue our exploration of this topic by considering slidewire generators. Here are the objectives. First, let's remind ourselves of the magnetic force on a moving charge in an external magnetic field. So here I have a positive charge and it's moving to the right in an external magnetic field that's pointing into the page. Recall that we use our right-hand rule here to figure out the direction of the force on this positive charge. So this is V, and I point the fingers of my right hand in the direction of V, and then I turn my hand so that my palm is pointing in the direction of the magnetic field, B, which in this case is into the page. That leaves my thumb pointing upwards, and that's the direction of the magnetic force on this positive charge that's moving to the right. The relevant equation here is that the force is equal to QV cross B, where Q is the magnitude of the charge, V is its velocity, and B is the magnitude of the external magnetic field. And the magnitude of that simplifies to QVB sine theta, where theta is the angle between V and B. In this case, theta is 90 degrees because V is to the right and B is into the page, and the force is 90 degrees to both of them by the right-hand rule. And just a reminder that because the force will continue to be 90 degrees to both of them, in this special case, we end up getting uniform circular motion because the force will always point 90 degrees from the velocity and points in towards the center of the circle, providing a centripetal force. Now imagine that instead of a single point charge, we had a conducting bar, and you can imagine that that conducting bar has many charges on it. I'm just going to draw one positive charge on this bar. Now imagine that this whole bar was being pulled to the right. You'd have exactly the same thing going on, and so this positive charge that I've drawn would experience a force upwards, and because this is a conducting rod, it can travel through the bar. That would mean, because this is happening to many positive charges on this conducting bar, we'd have a buildup of positive charge at the top. It also means that we'd have a buildup of negative charge at the bottom. You can imagine the negative charges getting left behind. Now that will create a positive end and a negative end to the bar. In fact, the positive charges will keep moving until the electrostatic attraction between the positive charges building up at the top and the negative charges building up at the bottom is equal and opposite to the magnetic force that is pushing these positive charges upwards in the first place. So as this bar moves to the right, we'll say it's moving to the right at speed v. Again, positive charges are being pushed upwards. Here, they're not able to move in a circle because they're constrained by needing to stay in the rod. But by building up positive charges at the top and negative charges at the bottom, we've created a potential difference across this conducting bar. And you can also imagine that if we were to connect this into a circuit via a wire, then we've got a positive terminal up here and a negative terminal down here, and conventional current would flow in this direction. So this is the principle behind a slidewire generator. And that's what's shown here. We have a metal rail here that's shown here with this sideways U-shape in an external magnetic field that here is shown going into the board. And then there is this slide wire, this conducting rod that makes a contact with the rail at these 2 points. So current can travel through these 2 points where the rod is connected to the metal rail. But this wire can move to the right or to the left. Here I'm going to show it moving to the right as we did in the above examples. So we have a complete circuit because we've got a metal rail and a metal rod, and we've also got the ability to change the flux through this loop. So this is a loop right here, and by, for example, moving the slide wire to the right, we are increasing the area of the loop and therefore the flux through it as well. Remember that our formula for the flux through a loop, the magnetic flux through a loop, is equal to BA cos theta, and as we increase the area of the loop, we therefore increase the flux through the loop as well. So the question asks us to find an expression for the magnitude of the induced EMF. So that's going to be equal to the time rate of change of the flux through the loop. And because I just care about the magnitude, I don't need the negative sign anymore. Well, the change in flux is equal to the change in the product of BA cos theta, and my denominator is the change in time. Well, the magnetic field strength is not changing, and cos theta is not changing either. Remember, theta is the angle between the normal to the loop and the magnetic field. So here, if we imagine the normal to the loop is pointing into the page, then theta is 0 degrees and cos theta is equal to 1. So that becomes equal to 1. And it actually doesn't matter if we made the normal pointing out of the page, which it could be as well, because then this would be equal to -1, and again, we just want the magnitude, so the negative doesn't matter. matter. So cos theta here is equal to 1, and that disappears, and the magnetic field strength itself is not changing. So I'm going to pull that out front, and I've got B times the change in the area divided by the change in time. To go further, I need to introduce some more variables. Let's call the length of this sliding rod from one contact point to the other, in other words, this length, L. And let's call the length of the loop from one end to where the slide wire is, X. And so now the area of this whole loop is equal to L times X. So the change in area is equal to the change in L times X. Well, L is not changing. It's only X that's changing. So I can rearrange to get this. I can pull the L out front because it's constant. And this part, the time rate of change of X, is just equal to the speed. And so this becomes BL times V. B, the magnetic field strength, L, the length of the slide wire from one contact point to the other, and V, the speed at which it's being moved. That gives us the magnitude of the induced EMF. So once again, if this is L and the magnetic field strength is B, and we're moving this at a speed of V, the induced EMF has magnitude BL times V. Now what about the direction of the current? Well, you can think about this in two different ways. One is the way that we started with at the top of the lesson, where think about a positive charge here and use the right-hand rule for a positive charge moving to the right in an external magnetic field pointing into the page. It's going to experience a magnetic force upwards, and repeat that, and you end up with a buildup of positive charge towards the top of the rod and a buildup of negative charge towards the bottom of the rod. And now, if they are free to move, which they weren't in the initial example, but now are because we've connected them into a circuit, the positive charges will move in that direction, and the current will go counterclockwise. So that's one way of thinking about this. The other way is thinking about it using Lenz's law. Here, by pulling this bar to the right, we are increasing the flux through the loop into the page because we're increasing the area of the loop. So we have a flux into the page that's increasing. Lenz's law tells us that the magnetic field that's going to be created by the current that we've induced in the wire is going to oppose the change. So it's going to oppose this inwards increase. That means that it's going to itself have to point outwards. The magnetic field that is associated with this current is going to point out of the page. Using the right-hand rule for that, you point your thumb out of the page, and your fingers are then going to curl in this direction, again telling us that the current is going counterclockwise. So by either of these approaches, you get the same answer. Let's finish by thinking about energy conversion and conservation in the slide wire generator. As you pull this to the right with speed V, you are doing mechanical work. Remember that work is the product of the force that you are exerting multiplied by the distance through which you're moving the bar through. And that work is going to show up as energy elsewhere in the circuit. If we imagine that the wires have no resistance, then we might put a load here, let's say that this is a lamp, and the work that you were putting in over here comes out as energy at the lamp, as light and heat. So you're putting energy in here as you do work, exert a force moving this bar through a distance, and you're getting energy out here. This is now a device for converting mechanical work into electrical energy. And the bulb is then converting that electrical energy into light and thermal energy. And you could divide both sides of this equation by time, and then you get power is equal to force times speed. Notice that if we take the load out, then we have less energy out over here, so we need to put less energy in over here. You can imagine now that maybe the wires have some resistance, so there's some energy out at the wire. But still, it would require a much lower force to move through the same distance, or a much lower force to move at the same speed, because the energy out or the power out is much lower. Another way to think about this would be what the experience of pulling this bar to the right would be like. Imagine that this was just a short circuit at first with no bulb here, and you were pulling this to the right, and then all of a sudden someone put a bulb in here. Let's say they flicked a switch that put this bulb into the circuit. You would immediately feel that it would get harder to pull this to the right, because now that the energy out over here has gone up, you have to do more work to supply that energy, and that means you need to supply a greater force to move the bar through the same distance or at the same speed. So even though they're not physically touching, you would have the experience over here of knowing when that bulb was brought into the circuit. So that's an interesting phenomenon that arises from this and helps us see how energy is being converted in the slidewire generator. So that's a look at slidewire generators.